Now we want to look at describing the region corresponding to the sphere given by this equation for x greater than or equal to 0, y greater than or equal to 0. So, and z is greater than or equal to 0 for every point that satisfies this sphere. That satisfies this equation because if z is less than 0, z minus 1 is less than negative 1, and its square is bigger than 1 already without adding the x squared and the y squared. Okay, let's think about where that sphere would be. Well, if you remember anything about the equation of a sphere, this is standard form for the equation of a sphere centered at 0, 0, 1. So this is a sphere of radius 1 centered at 0, 0, 1. Where is 0, 0, 1? Well, it's going to be right here on the z-axis at z-coordinate 1. Now if we got x equals 1 out here and y equals 1 out here, don't have these scales quite right, so it's going to look a little bit like an ellipse when I draw it, but that sphere will have a radius 1, centered at 1 means it'll go up to 2 and down to 0. So what we have, if you want to visualize it, is just a sphere that's sitting on the origin. It's sitting right directly in contact with the origin, so it's sitting above the xy plane. And its only intersection with the xy plane is the origin. Now we might as well draw the trace of the sphere in each of the three dimensions. The trace, or each of the three coordinate planes. The trace in the YZ axis is just x squared plus z minus 1 squared equals 1, and it's not x. X equals 0, so that should be y squared plus the quantity z minus 1 squared. I'll fix that in a minute, but let's try to live with it for now. And that's the equation of a circle of radius 1 centered at 0 on the y, 1 on the z. So it's simply a circle of radius 1, which means it's going to come out this far. And this thing's going to be somewhat distorted, but okay, it's kind of squashed down because of the difference in the scales, but this is supposed to be a circle centered here. Radius 1. It looks more parabolic. Not the greatest picture I've ever made. Probably not the worst. Now I said I do the trace in each of the coordinate planes. Well, I can do the trace in the XZ plane. It looks like I've labeled my x-axis as Z. I'm going to write over that, but we'll fix that again in a minute when we pause. We can come up 1 unit above this point. That puts us about here, and our sphere will come out like this. It's going to have to come down here, come parallel to the z-axis here, then continue down like so until it comes around tangent to the x-axis. Now that looks really distorted. This is not a very good drawing, but we can still use it to represent the situation. And in a lot of cases, our drawings are going to have to be representative. It's going to be difficult to make accurate drawings of many of the surfaces we'll be looking at. Okay, and this projects down here. Now we talked about the trace. Okay, this is the xz trace, and that's x squared plus z minus 1 squared equals 1, centered at z equals 1, radius 1. That looks a little better than this does. Now the XY trace is just the origin. Okay, the XY trace is simply the origin. And that's not actually very helpful because we want a region in the XY plane above which this sphere lies. Now, it's also possible to project the sphere back into the XZ plane, for example, or into the YZ plane, bad drawing notwithstanding. But by modeling this integral based on the XY plane, we're going to be able to deal with the situation where the surface above is not represented by one function. In this case, it'll turn out to be represented by two functions. And that's a situation we still call simple, but let's go ahead and do it, and then we'll talk about what we did. Remember the statement we made originally. We have some three-dimensional region in general that lies above some region of the XY plane with the property that every point of the three-dimensional region lies above some point in the XY region, and every point of the XY region has a point or points of the three-dimensional region lying above it. Our first examples involved what we called simple surface above the XY region. That wasn't a very good term to use, but that indicated a region indicated by single function z of xy. Single valued function z of xy, so there was a single value z at which we encountered the surface. And the region was considered to be everything between the xy plane and that surface. Now if we take a region of the xy plane, somewhere in the first octant, not too far from the origin, this ball is sitting on the origin. It has a radius of 1. This point is a lot closer to the z-axis than 1, so if we move up in the direction, in the z direction, we're going to hit the surface at some point. If we continue to move in the z direction, at some other point, we're going to hit the top of the surface. So here's a point xy in the plane region for which a vertical line, and that's kind of a vernacular term, that just means a line in the z direction in this case, and so that terminology should be implicit. Intersects our surface at 2 points. This is going to mean that when we partition whatever region we end up with in the xy plane, we're going to be partitioning a z interval that doesn't start at 0. Now there's nothing wrong with that. The z interval will start here and end here. And we're going to be able to pretty easily determine what these two z values are based on the x and y values, but we're not going to worry about that just yet. We want to keep that in mind, but first we have to figure out where the points are. That the points from which a vertical line will intersect our surface in at least one point. And with this sphere, I think we can understand that in most cases it's going to intersect the surface in 2 points. Now it can actually be kind of an art and a science to figure out where some regions project into the xy or the xz or the yz or some other plane. In this case, it's fairly simple. The smallest possible value for z minus 1 is 0, which means that the biggest possible values of x and y occur when x squared plus y squared is 1. So I could say that z minus 1 squared is greater than or equal to 0. So x squared plus y squared is less than or equal to 1 minus z minus 1 squared. For z equal 1, we get the maximum possible bound on x and y. X squared plus y squared is less than or equal to 1. And as long as x squared plus y squared is less than or equal to 1, the vertical line z it's not z, it's x. I'm going to have to stop and fix a couple of things here. Okay, a few touch-ups here. The vertical line, I was going to write the equation of the line, but that was going to get too complicated, have to parameterize it and so forth. The vertical line above x, y is 0.